Okay, in this particular section, we want to talk about an important concept, um, and that is the mathematical concept referred to as an exact differential. If you recall, what we have said all throughout this study of thermodynamics is that the thermodynamic state of a pure substance requires the knowledge of two independent properties. Upon those two independent properties, we then can determine all of the rest of the thermodynamic properties. And so it turns out because of that, we can then say that a thermodynamic property can act as if it is an exact differential. And an exact differential would mean that the magnitude of the property depends on the state, the location of that property on a thermodynamic diagram. And it does not mean that it depends on how one got to that particular point. And we have seen that throughout our discussion. And so if we can assume that a thermodynamic property can be written as a function of two independent thermodynamic properties, we could then say that the property itself can be written as an exact differential. And so in mathematics, when we talked about exact differentials, we said that there was a function z that was continuous in the space or in the variable x and y. So if we have an x and y space, the function z is identified by knowing the x and y, and it's continuous in that particular region. And if that function itself is an exact differential, we then can say that the dz is equal to the rate of change, the partial of z with respect to the first independent property, holding the second independent property constant, dx, plus then the partial of the z function with respect to the second independent property, zy, holding the first independent property constant, dy. And so we sometimes write this in math as these two partials being written as capital M and capital N. Now, the test for exactness, whether or not this actually is an exact differential, holds that the cross partial of each of the terms are equal to each other. Or another way of saying that is the partial of this m with respect to y at constant x is equal to the partial of n with respect to x at a constant y. And so if we were to put the value in for m, in essence, all we're really saying is the second partial of z with respect to x and y. And so is equal to the partial of z with respect to y and x. And so that is the test for exactness, is if this holds. There are two other relationships that also hold and for an exact differential, and that is the partial of the x with respect to y at constant z times the partial of y with respect to x at constant z is equal to 1. And also this chain partial, the partial of y with respect to z, the partial of z with respect to x, and the partial of x with respect to y is equal to -1. And so if we have a function and we feel like that function is an exact differential, and that function can be written in terms of two independent properties, we then have this relationship among the various thermodynamic properties. And so where does that come into play? Well, it comes into play when we start looking at the pressure volume and pressure temperature charts for a pure substance. If we are plotting pressure versus volume, we know that the third variable then is the temperature. And so we remember in our first thermo that lines of constant temperature then, which are called isotherms, then can be mapped on this plane. Obviously, here is the isotherm that goes through, which corresponds to the critical temperature. And then once we get lower than that critical temperature, we see that the substance goes through the subcooled region. It hits the dome and it goes across, and then it comes out into the superheated region as an isotherm. And so when we have that, and we're very familiar, hopefully, with this particular chart, what this tells us is for substances that behave like this, we see that along an isotherm, along a constant temperature, we see that the pressure with respect to volume, the partial of pressure with respect to volume, is less than 0. That's a line that has a negative slope. And so that partial for the gas has that relationship. And so what does that tell us? That tells us that if we have a substance and we're holding it in a constant temperature process, that as we change the volume, the pressure is going in the other direction. And that makes sense. If we opened up, if we had a tank full of gas, and if we kept the temperature constant and we made the volume twice as big, the pressure would go down, and vice versa. And so that basically corresponds to the fact that this partial of pressure with respect to volume is a negative number. What is it under the dome here? We see that the change in pressure with respect to volume at constant temperature is equal to 0. And that is because we know that as we went from the subcooled point to the superheated point, volume does change, but the pressure doesn't change. And so that would correspond to a line of constant of 0 slope, just like it was at this point right here. And so that's the conclusion we can draw from the PV diagram. From the PT diagram, our third variable is volume. And so the lines of constant volume are called isomeric lines. And so a line, if we're over here in the vapor region, a line of constant volume would then, as one would see, would have then a slope which is dp dt. The change in P with respect to T at constant volume would be a positive number. These are all positive slopes. And so for most substances, then we see that that particular derivative, that particular partial, is greater than 0. In this line here, we had, a solid line that corresponded to the dome, and that solid line went from the triple point to the critical point, and we remember that as just being the pressure temperature saturation relationship associated with a substance that goes through the two-phase process. And so that, at a given pressure, that tells us what the condensation temperature is, the evaporation or the boiling temperature of a substance. And so we see in the saturation region, where pressure and temperature are related to each other, we see that there would be a relationship corresponding to how much does the pressure change as the temperature changes. And so that would basically be the slope of that particular line. Okay, so now with that understanding, we now can look at various other properties and use this concept of the exact differential to our benefit. Okay, if you remember back in section 6.3, two equations were developed, and we referred to those as the TDS relationships, the temperature, change, and entropy relationships. And the first one was TDS is equal to du minus or plus PV. So there were two parts. And the second one was TDS is equal to DH minus VDP. And if you don't remember them that way, possibly you remember that the du was written as dv or c sub v dt, and dh was equal to c sub p dt. And so you might have remembered them in that particular fashion. But if we rewrite these equations in terms of internal energy and enthalpy on the left-hand side, we then can see that internal energy and enthalpy can be functions, can be written as a function of entropy and specific volume. And here we see the entropy and the specific volume, and we have that exact differential associated with an exact differential for the internal energy as a function of two independent variables, S and V. Likewise, this equation here for enthalpy, we can say that enthalpy is a function of entropy and pressure, and we can then say that the exact differential shows the relationship between how enthalpy changes with respect to changes in entropy and pressure. And so that's, that basically tells us, if you kind of draw the conclusion to that by going back here, okay, going to and drawing the analogy between what an exact differential in one variable means with respect to the other variables, we can now say that if this is du, then this coefficient here, t, is really related to the partial of u with respect to s at constant v. And so we can now say this measurable thermodynamic property of temperature is related to how internal energy changes with respect to entropy for a constant volume process. And so we are drawing an analogy between these properties that we might not know much about, internal energy, entropy, and volume, with things that we do know about, and that's temperature and volume. And so we'll approach that in just a second here. Some other functions that have been introduced that show up in some of the other sections are some functions. One is called the Helmholtz function. And the Helmholtz function is a thermodynamic property, and it's just related to internal energy minus Ts. And the Gibbs function, and this is used a lot in combustion systems, the Gibbs function G is just equal to H minus Ts. And so in both those cases, if one said that the Helmholtz function was an exact differential, one can then take the partial or the derivative, the total derivative of this function, and determine that it's related directly to the other properties. Okay, it's basically utilizing this whenever we took the total derivative of u, we substituted this, but we can show that these other thermodynamic properties, which are total differentials, are related to, and once again, you see that we are trying to put them into functions of temperature, volume, and pressure that we know how to measure. And so we're trying to take these other properties that we don't really know how to measure. We don't know how to measure entropy. We don't know how to really measure internal energy or enthalpy, but we can relate them to measurable thermodynamic properties. And so with all of that in mind, then, we can go through and determine a whole series of property relationships from those exact differentials. And these are listed in table 11.1 in your textbook. And in essence, what they are attempting to do is to try to relate changes in the various thermodynamic properties under certain conditions and how they're related to measurable properties. And so in this particular case, from knowing that H is a function of entropy and pressure, we draw the conclusion. We went over to here and we said then that must mean that temperature is related to the change in internal energy with respect to entropy at constant volume. So each of these terms then corresponded to a partial. The same thing was done for this equation here, for the Gibbs equation. And we saw that relationships between those. And then some additional relationships, again, brought about by the various exact differential relationships and the like. And so we see a whole series of interactions and relationships among the thermodynamic properties. And so what this allows us to do, it allows us then to establish tables for some of the thermodynamic properties such as entropy, internal energy, enthalpy, based on measurable quantities such as temperature, pressure, volume, and possibly the CCP relationships. Okay, so in the textbook, there is an example, and we developed this relationship, one of those Maxwell relationships. And if you recognize this Maxwell name, these relationships are very similar to the same Maxwell electromagnetic relationships developed in electricity between the electromagnetic E and H. So magnetism and electric fields. But if we, in this example in the textbook, they said that there was this particular relationship between entropy and volume. And so we see entropy and volume at a constant temperature. So this was one of the relationships, and we found that it was equal to or related to how pressure changes with temperature at constant volume. And so they're asking in this particular problem, since the Redlich-Kwong equation of state was a complex an equation for pressure, temperature, and volume, could you not use that Redlich-Kwong equation of state, obtain this partial, and then have it represent the change of entropy with respect to volume? And so what that then allows us to do is it allows us to evaluate the entropy value and how the entropy is related to volume as a function of pressure and temperature. And so again, that example problem allows us to look at the various relationships in that fashion. And so what we now have, by doing what we just did, we now have a complete description of the thermodynamic state of a pure substance. We saw that these other thermodynamic properties of internal energy and enthalpy, plus the two that I just introduced, are a function of two independent properties. And those two independent properties are could be temperature, pressure, volume, and in addition, entropy. And so by knowing that, then all the properties of interest can be determined by either differentiation or a combination of the various thermodynamic functions. Okay, so we will stop at this particular point. When we come back, we're going to start looking at some of the changes, some of the things that are associated with phase changes, how entropy, internal energy, and enthalpy changes as we go from one state to another state. And we're going to begin by focusing, first of all, on a change of phase. What happens when we have the substance going from the liquid phase to the solid, or liquid phase to the vapor phase? Can we write some relationships associated with that?